Alright, good evening everyone. My name is Jaya Bhanu Rao. As I've mentioned earlier, so at the moment I'm doing my research studies at the Newcastle University, majoring in behavior-based control. Behavior-based control is more like sort of intelligent controllers for various applications, but for this particular research that I'm working on is powered wheelchairs. Okay, let us go a bit back before the presentation starts. Prior to this, there are a lot of behavior-based controls has been implemented in the mechatronics fields. And one of the challenges that we've gone through is avoiding obstacles. It's always become a greatest challenge among researchers lately and also in the future. One of the main reasons is because of the change in the environment, which are always not stable. And then another reason is factors that influence, such as dynamic obstacles, which is also a great challenge, particularly in cluttered environments where there is a big crowd, for example, such as in the shopping complexes. So we personally have seen many users of wheelchairs trying to move around or find their way out within the cluttered environment. But has any one of you have driven a wheelchair before? Anyone? A project. But have you personally sat on the wheelchair and have driven? I did. You did, yeah.
I used it for 2 months.
How do you find it personally when you try? Is it a powered wheelchair or the manual? Oh, hand-driven, yeah. But the one I have at the moment is the powered wheelchair. Pius and Gilner is from VTC Edicare from UK company. And then I've driven personally and ended up a lot of accidents. Banging to the doors, banging people who passing by. And it's not so easy to maneuver by using a joystick. So my project here, what I did, I dismantled the original controller because it's just an open loop and it does not have any form of intelligence. It's just a proportional controller. So my research is mainly to modify the wheelchair and use an intelligent controller. But bearing in mind, there are a lot of researchers who have been working on these wheelchairs. They have what they call a robotic wheelchair, and some they call it as a shared intelligent powered wheelchair controls. You can see numerous papers that can be found on the internet. But as in my case, I would like to give the priority for the users. If the robotic wheelchair brings you wherever you want to go, does that scare you? Scares you? Scare means like, will you feel nervous? You just sit on the chair and then all of a sudden, okay, you just press on location, okay, I want to go to the toilet. So you'll be going to the restroom all the way without, knowing, okay, do you trust your own driving machine? No. Driving is you still have the control when you drive a car, for example. But what about a car that drives you wherever you want to go? I think BMW have done that before, one of the research, where it's like kind of a robotic car. You just press the location and then, but sometimes, oh, I'm scared. You know what I mean? If you trust your driving machines, no problem. All right? Because we always want to have the control. And the intelligence be taken over by the car. For example, in the BMW have done some kind of a collision avoidance as well. When it goes too fast, when you tend to fall asleep, when the car approaches too near, it automatically stops.
It's already standardized.
Standardized, yeah. Yes, exactly, yeah. So that is what I've read, So it's like a standard feature now for all the cars. So this is to minimize the collision, to reduce the accidents. But what about for wheelchairs? Can we make the wheelchair as a fully autonomous? There are some limitations that we can have to think in this area. Firstly, what sort of sensors that we're going to use? And then what are the limitations that they do have? For example, most of the wheelchairs in researchers, they can't even reach to a state of commercialization. Why? For example, we can use a GPS to monitor the movement by using the SLAM. mapping, localization. But what is the limitation of the GPS? If it goes into the buildings or go into the jungle, that's it. The signal will be distorted. And what will be the case of the user of the wheelchair? He'll be stranded in somewhere. You know, that scares you entirely. Oh, I can't trust this machine. Might as well I override the control, I drive myself wherever I want to go. So bearing that kind of environment, but the technology, yes, is already there, but still people are not that confident, in other words. All right? So what I'm doing at the moment here, I'm trying to create a semi-autonomous. That means I have a two intelligence, human intelligence as well as the wheelchair intelligence. So now the challenge that I'm going to go through here, how the intelligent controller will communicate with the humans. That is the greatest challenge. I want to go to that spot, point A. The wheelchair said, no, you can't go because there's an obstacle. He diverts you. No, I still want to go there. Can you see that difference? So, and then you feel like, oh, this is really annoying me. All right, so let us go through what I've done so far, and then if any questions in between, just keep it to the end so that it will be easier for everyone. Yeah? Okay, right, let's look at the, okay, I don't know how to switch. All right. Firstly, when I started with this project, I have to make a lot of assumptions. Okay. The first assumption is because my research, I focused mainly on the indoor. Why indoor? I did ask a friend from Sikh. He said that there are sensors, the new technologies where it can be used in the outdoor environment because of the extreme weather conditions. And these sensors are extremely very expensive. Easily can cost more than 3,000 British pounds. Okay, so I don't know how much. So you can imagine that. If these sensors are extremely expensive, then how do you want to commercialize them? And the end users will be the handicapped people or disabled people. Is there anyone willing to invest a lot of money in buying the most expensive wheelchair? Definitely not. As far as the researchers are concerned, yeah, they're very, I would say, enjoying themselves, to come up with the new innovations. But by the end of the day, your wheelchairs are not sellable, and then you will lose in the market. It's just too expensive, right? So this is the reason why I have to downgrade myself to include the human as a main controller, and the intelligent will do the rest of the job. So what is the most key factor here? I have to take into consideration the user's level of comfort. If we are driving the wheelchair, I personally have driven the wheelchair. If you want to move, you do not know when is the time to maneuver the wheelchair when there is an obstacle approaching. If assuming that a dynamic obstacle is approaching, there will be an instance whereby you want to move to the left and the other guy wants to the right. When it comes to near, you will come a situation, a stage of confusion, we call it. You'll be doing like this. So he's going there and then you are going here. Have you ever came across, even among the humans, when we walk in the shopping complex? Oh, excuse me. All right, okay. Can you see that? So these are the level of confusion. So if you do that in the wheelchair, what is going to happen? And that guy will cause some level of discomfort, and he will get some kind, like some of us might have motion sickness. I can't read while the car is moving. I feel like throwing out. Does anyone here have that kind of effect? Motion sickness is very bad in me. So I can't read even a text messages in my car. It's that bad, Some people, yeah, I'm quite jealous with them. They can read even novels, Wow. That you can even read maps in the car while the car is moving. But for me,
While driving?
no, what I mean, when you are sitting as a passenger. Not, of course, you can't drive. Even I'm driving, I just try to glance through very quickly. Also a problem. That's a level of sensitivity that I'm going through. Okay. Some of us even have a flight sickness. No, I mean, if you go to a flight, you get giddiness, and all this kind. You said just put the materials away, get something, and then just goes off. So these are the things. Everyone has a different level of comfort. So this is what happens as you get elderly, and then these are the things that I found out that they will have this kind of level of discomfort if the wheelchair is moving left and right, and you feel like a bit giddy. oh my God, I'm not going to drive this wheelchair. Okay, I'll ask an assistant, to push my wheelchair. So this is one of the factors that I've taken. And then my main objective of this research is to ensure that the user can successfully avoid the static and dynamic obstacles comfortably without any, to minimize the sharp shifting. We can see the obstacle is approaching and then you tend to move very quickly. All of a sudden, you might be distracted, some kind of sports, oh, that's a very nice picture. But you are not aware that an obstacle is coming in front of you. And all of a sudden, you notice this, oops, you try to switch your joystick, all of a sudden, that can cause a sharp shifting. So it's always better to incorporate an intelligent controller to assist you in overcoming this obstacle in a very smooth curve. You try to minimize, we cannot expect a very perfect, but you try to smoothen the movement of the collision avoidance. Okay, so these are the things that I have discussed earlier. So my task is to develop a robust algorithm. It's just like a black box. So this is a low cost. I can fit to any wheelchair without major modification. So this is my intention to develop this wheelchair. Some wheelchairs in the NHS in UK, they tailor-make the wheelchairs with respect to customers' requirement. Some they want fully robotic, some they want just powered wheelchair. So they do 100% of the movement. And then what I've tried to use here is very basic softwares. I've tried to simulate some of the functions in MATLAB, and then I'm using Linux-based systems to obtain the real-time systems as much as possible. And then I have used the wireless joystick, Cytec Evo, to simulate these movements. But bearing in mind, I did make some assumptions that at the moment I'm using laser rangefinders, which has very limited detection. It's about 240 degrees, and it's only one plane. I'm using a Hokuyu laser rangefinder with a limited 2D scanning area. So whatever objects that falls below the scanning level considered not to be taken at the moment. And finally, C came up with a 3D scanning by incorporating another servo so that it can have a 3D scanning. So I'm in the mid of finding an alternative sensors as well to get the input from the sensors. Like there's one more Kinect, this one, from Microsoft Kinect. It's one of the camera that I'm planning to look into the system. Another one is Bumblebee XB3 camera as well. And Kinect is, I think, is the most cheapest. It can cost about 140 pounds. But Bumblebee easily more than 3,000 pounds again, so it doesn't come cheap. So I have to look something at the low cost. But for the time being, I'm just using one sensor to get the algorithm built up. And once it's successful, then it's just a matter of input. You can put as many sensors as you want, and then my black box will do the rest of the job in avoiding the obstacle avoidance. Okay, this is my the control architecture. So I did mention earlier about the behavior. So what are behaviors? Behaviors, as what is described by Ronald Arkin from his architecture, is that behavior is to mimic human control. For example, some of them are listed here. Go to the target. It can become a behavior. So I want to go to that spot. So that means that is your behavior, that I want to go there. What about the avoidance? I want to avoid the obstacle. That is another behavior. And then follow the leader. For example, in the crowded environment, we want to go to that kiosk or the booth. But what happens? People are obstructing you. And there are times we want to overtake them. But the time you want to overtake, again, there's another person crossing by. And you'll be very distressful. So what? You have no option. So what you have to do? You have to follow the person who's going in front of you. So you take an advantage of the person because he's guiding you. In other words, he's creating a way for you to lead to your destination. So these are the things that I've collected some of the information from the actual human behavior and I incorporated in the system. And then the last is definitely is emergency stop. So when the emergency stop applies, for example, we want to exit the door, and we can't see whoever coming from the outside. If suddenly it goes very fast or in a very consistent speed, there will be another wheelchair driver or another person running, there are chances for the collision to happen is very high. So we want to minimize this effect. So there is one behavior, I put it as an emergency stop. So we look at that in more detail later on. But my focus of this today's presentation is only the one that I've listed. So this is my big project actually for the 3 years of my study. But today I'm just going to talk about the obstacle avoidance, static and dynamic. All right, so laser rangefinders are standard components, but the challenge here is how you want to read the data from the laser rangefinder. We can plug it in Windows-based platforms. There's a lot of software available, but as far as the Linux system, I'm using the Ubuntu 12.04 LTS long-term support. You have to create your own drivers, and then you have to write your own codes. This is what I did by using a very simple algorithm. I'm using the laser data, they call it laser data clustering. I'll show you how does that work later on. And then the kind of specific algorithm I'm using here is known as point distance based segmentation. So this has been the most popular among the researchers. All right, so I've done some very simple test experiment to determine what's going. So this is the laser rangefinder, as you can see in the light blue. Can everyone see that? Yeah. Right. So what happens when the object appears? So you can see there's some kind of a segmentation being appeared. So just a square box. On the other hand, you can see the pattern of the object. So the green line shows the segmented path, and then the gray line shows the box, the laser distance from here to here. Right? And then what if we have another object in the scene? So you can see the laser actually can differentiate between multiple objects. So this is a software called a player stage simulation. There's another one more known as gazebo. So gazebo is getting very popular nowadays. But gazebo can be simulated in terms of a 3D, but it is a computationally intensive, and then it slows down the system. Gazebo is very good for simulation, but PlayStation is very good for 2D, and then it can be transferred directly to your computer controller. So you don't need to do any manipulation of the interface. Player stage.
Player stage.
Yeah. So something. It's an open source. Yeah. By the way, I forgot to mention that all the software that I'm using is open source, so I don't buy any license. And then bearing in mind, open source is you have to take the risk. All right. Sometimes the developer of the software does not maintain. And then recently I had an experience where I installed Ubuntu 13.10, and last year January, all of a sudden they closed down the support, and now I cannot run it at all. So I was forced to upgrade to Ubuntu 14.04 LTS. But end of the day, 14.04 doesn't support the play stage. You see, these are the complications that you have to bear in mind. There are other softwares, robotic, Microsoft Visual Studio, but again, that is not a real time. So I have no other excuse, but have to use the PlayStation to develop the algorithm. Okay, next, how it actually avoids the collision. Okay, my apologies because it's very too scientific, so I'll try my best to explain how it works. The method that I'm using, what we call as a collision avoidance here, is the collision con approach. So the laser rangefinder will try to detect the object, and it forms a cone. So anything that falls within the cone, it shows that the chances of the collision is very high. And then I don't want to end up coming very near to the obstacle, so I've created an imaginary circle around the obstacle so that we can have some safety margin to avoid the obstacle. So this is the method that has been developed by previous researchers. So I'm just trying to make use of it, and then to avoid the collision avoidance. So this is for the a circular shaped object, but what of the irregular shape at the other end? So what the laser rangefinder will do, will try to scan the starting and the ending point of the obstacle, and then automatically my algorithm will create, we call it a circle fitting method. So you try to create an imaginary circle, so it surrounds the obstacle, so that any irregular shapes will be within that circle. So the cone can be easily formed. So this is a very straightforward method. And then the few experimental works that I have done is try to avoid the static obstacles in the beginning. See on what you can see on the top picture here. So I've created an imaginary obstacle. So the user will try to avoid it, but bearing in mind this is not the intelligent yet. The user is trying to control it manually first. So you can see that the pattern of the movement is very rough. You can see that it's very rough. So what's going to happen? This is what causes the level of discomfort in terms of the velocity. Suddenly it comes very fast because it's not easy to control the joystick movement. Sometimes we accidentally make it very fast because of the dexterity. Because when you get older, you have a very less force on your hands to control. You kind of sort of like jittery. Okay, so it's not so. So this is what causes the movement. So I deliberately created a signal to simulate the jittering movement because I'm not old enough to create. I try to do it. So, but this is the best I can get, you know. So, and then finally you can see the graph on the right hand side is one of the degree. But bear in mind the maximum speed that I've fixed here is 1.7 meters per second. This is according to the Ministry of Road Transport Act in UK. So any scooters or mobile vehicles that is running on the pavement or on the public, the speed must be limited to 1.7 meters per second. So I cannot go anything beyond that. So that's my limitation. Right? So and then you can see how you can actually go around trying to avoid the obstacles, and you can see the pattern of the movement is simply not very smooth. And this is what causes the jerky movement. And as for the dynamic, again you can see. So when you do it manually, you can see a lot of difficulties. You can see that it's not smooth at all. Okay? But when it comes to a very low velocity, you don't feel much. But at a higher velocity, at 1.7, you can see a very sharp shifting. So that causes a bit of giddiness, you know, especially for the user. So I can see that this is another object approaching. So it's trying to use the cone method to avoid it. So my task is to improve this collision cone approach by using a fuzzy logic, fuzzy inference system. Okay, and then this is what I was talking about, the emergency. So there will become a situation whereby known as a blind spot. You are trying to ride the wheelchair, but you can't see what is going on. And then bearing in mind, there is some limitation for the laser rangefinder. It cannot go through the walls. This is absolutely a very critical situation. So when it comes to a point, this is where you can see the wheelchair not supposed to hit another object that is approaching. So this is the one that we are driving, the one in red in color, and then the orange is another wheelchair user is trying to come through the door. And at the same time, you are also trying to exit. So the emergency stop behavior will try to slow down upon reaching the zone of the laser rangefinder, and then you try to reverse it back until the blind spot is cleared. So this is some sort of level intelligence that I've incorporated. Again, before I go any further, there is some challenges here. If I want to go to that obstacle, the intelligent controller must be able to read the user's intention. So how does it read the intention? Does it read his mind? No. I don't wire the brain of humans into the controller. Okay? So this is the challenge. So there's only two inputs, the velocity and the direction. So with these two, I must fully utilize only with the two inputs to feed into the system and try to read what the user wants to do. If the laser rangefinder can be segmented, so anything that you move in the joystick has a 4 quadrants. So when you move forward, the angle is 0, that means you are fully going to the forward direction. So when the user tries to go to 0, that means you really want to go to the object. At this point, the controller will say that, okay, the user wants to go there. If he wants to avoid, the user must tilt the joystick more than 10 or 20 degrees. Then the controller knows, yeah, he wants to avoid. So then it overtakes the controller and tries to help him to avoid. At any point, if the user lets go the joystick, it goes to a 0 position. That means the wheelchair will come to an halt. It does not go anywhere for safety reasons. So the user has in other words, a level of control of how he wants to avoid. If he wants to overtake fully, even he lets go the joystick, but the wheelchair still goes. That's very scary. And so he have like 2 grams. So he has the some sort of feel of driving the wheelchair. So we do not want to disappoint the users to have that feel of driving. Okay, so I've developed, so I've used a MATLAB to come up with the fuzzy logic. I had some membership functions. So I'm using 2 inputs. As you can see, when there is an object, the laser rangefinder tries to scan the object. The closer it gets, the angle, I'll go back a bit back, just to show, alright, so if this, assuming that this is my wheelchair, the closer you get, this angle becomes wider and wider. Can you imagine that? So it becomes something like this, bigger. So the further you go, the angle becomes smaller and smaller. So I've taken that advantage as one of the input. So one input is from the angle over here, another input is the velocity, right? Because of course I can't take the distance because the distance varies at every here, it varies, as I've seen in the previous over here. Right? So I can't take the distance. So in other words, I just have to take the start and end point. So the velocity and the angle over here. So the closer it gets, the angle gets more wider. So if it's more further away, the angle is a bit smaller. The cone angle is smaller. All right. Okay. All right. So, so these are the things, and then I've used the distance and the angle as my inputs, and the output is the behavior. So the behavior I'm using here is the actual output speed, the final speed of the fuzzy inference system. Okay. So we have 2. So I've just actually simulated this on the MATLAB by using the fuzzy logic toolbox, right? And then the greatest challenge is Linux does not accept the MATLAB codes, so they still have a very big difference. So ended up I have to write my own code in C for the fuzzy logic. So it took me ages from scratch, you know. So that's in player stage. So I just used the basic C code in order to write the output of the membership functions. All right, and then in that principle of getting the object being avoided with the collisions, I've used a few other parameters in it, which is the minimum time to avoid the collision, and then I see also minimum distance to avoid the collision, also the total travel time. So these are some other factors that are incorporated in my algorithm to judge whether the collision takes place or not. So the final objective is to ensure there's a smooth movement. All right, so what happens next? How to measure those things? So I'm using what you call as a performance metrics. The path left, the total travel left, and then I'm using the level of smoothness by using a bending energy. So the bending energy explains how much the deflation between the original direction to the diverted one. So by using that measurement, you can judge the level of smoothness in terms of movement and definitely the number of collisions. Okay, so this is my final results. So what you can see here by using the FRS system, so the one in red in color is the joystick. So the user can happily go front, back, but the fuzzy system tries to limit the speed of the wheel, the final wheelchair. So it creates, the moment you're approaching the object, you try to make the movement, the velocity become slower and slower until you come to a halt. And then this is the obstacle avoidance with the FIS. Again, you can see beginning, the velocity of the wheelchair and the velocity is about the same, almost the same. You can see compared to the previous graph, there's been a lot of distortion. So by using the FIS, I can minimize the level of distortion. And then you can see, so when the object is being approached, you can see that the user can do whatever he wants. You say that, oh, I can stop when it comes to the near object, but the FIS, the intelligent controller, does not allow. You say that, I'm sorry, I can't allow you. There's a potential collision in front of you, so I have to limit the speed. And on the other hand is the turn rate, how much do you turn. So it determines whether you want to avoid the collision or you want to stay in the direction. If I want to go to this object, I can go, but I have to stop. All right, because I want to reach something from the bench. All right, so finally, okay, that's my conclusion. So there's still a lot of work that has to be done. So now the next stage is I have to get this data and then put it in the actual wheelchair and then try to make it work. And then another challenge here is the outdoor. So as I said, most of the factors that involved is the type of sensors that I'm using to get the data. But my aim, objective is to develop the black box so that I can actually build it, and then you can use as many sensors as you want as long as it's in the intelligent controller. Okay, thank you very much. That's all for now. Okay. Any questions?
Is there any questions?
During the installation, how did you deal with dynamic objects?
The dynamic object, what it does, the laser rangefinder will detect the speed of the obstacle, speed and the direction of the dynamic obstacle. So from there, if there are times the obstacle maybe wants to go another direction, so my laser rangefinder actually can measure the velocity, just like speed trap cameras, right? So you put in the camera, and then you can see how fast the car travels, the speed trap. So I'm following the same concept. So when the dynamic object comes, it knows if it comes in its own direction, and the turn rate will be greater. If it goes to another direction, then you'll just turn a little bit just for a safety reason. Then it just bypasses. So that is the method that I employed. Oh, yes. Oh, thank you. Oh.
Good job. Yeah, I did something like that actually for the American Army in '95, but that was actually with moving helicopters.
Ah, I see, right.
Yeah, so what we did actually, we asked actually a pilot, a human pilot, to try to control the helicopter to avoid some moving obstacles, birds or another maybe thing. And we have a neural network that learned from that and built the fuzzy actually rules for, and we tested that, it worked. Maybe I recommend actually that you go to this mode-based actually, that is he conservative, is it dangerous, is it so?
Yeah.
It's going to change the rules for you.
All right.
But nice work, I like
Okay,
that.
thank you very much.
Okay, good luck.
Any other questions?
Any other question? So let's give him a round of applause again.
Thank you very much.
Thank you.